Estimating Single Population Parameters, Part 2. In the previous video, we have discussed the basic trade-offs that are present in all statistical estimations. The desire is to have a high confidence level, a low margin of error, and a small sample size. The problem is that these three objectives conflict. For a given sample size, a high confidence level will tend to generate a large margin of error. For a given confidence level, a small sample size will result in an increased margin of error. Reducing the margin of error requires either reducing the confidence level or increasing the sample size or both. A common question from business decision makers who are planning an estimation application is, how large a sample size do I really need? To answer this question, we usually begin by asking a couple of questions of our own. First, how much money do you have budgeted to do the sampling? And second, how much will it cost to select each item in the sample? Keeping in mind the estimation trade-offs discussed earlier, the issue should be fully discussed with the decision maker. For instance, is a sample of 200 sufficient to give the desired margin of error at a specified confidence level? Or is 200 more than is needed to achieve the desired margin of error? Therefore, before we can give a definite answer about what sample size is needed, the decision maker must specify her confidence level and a desired margin of error. Then, the required sample size can be computed. Let us look at this example. Mission Valley Power Company, or MVP, in Northwest Michigan, which has more than 6,000 residential customers, and in response to a request by the Michigan Public Utility Commission, MVP needs to estimate the average kilowatts of electricity used by customers on February 1. The only way to get this number is to select a random sample of customers and take a meter reading after 5 p.m. on January 31 and again after 5 p.m. on February 1. The Commission has specified that any estimate presented in the utilities report must be based on a 95% confidence level. Further, the margin of error must not exceed plus minus 30 kilowatts. Given these requirements, what size sample is needed? To answer this question, if the population standard deviation is known, we start with equation 8.3 from the previous video, which is the equation for calculating the margin of error. We next substitute into this equation the values we know. For example, the margin of error was specified to be 30 kilowatts. The confidence level was specified to be 95%. With 95%, the z value is 1.96. This gives us 30 is equals to 1.96 times the population standard deviation divided by the square root of the sample size. We need to know the population standard deviation. MVP might know this value from other studies that it has conducted in the past or from similar studies done by other utility companies. Assume for this example that the population standard deviation is 200 kilowatts. We can now substitute the population standard deviation to our equation, leaving us with the unknown variable n. And we can now have a single equation with one unknown, which is the sample size. Doing the algebra to solve for n, we get n is equals to 171 customers. Thus, to meet the requirements of the Utility Commission, A sample of 171 customers should be selected. If MVP feels that the cost of sampling 171 customers will be too high, it might appeal to the Commission to allow for a higher margin of error or a lower confidence level. So in general, equation 8.6 is the formula for computing the required sample size. Take note that the formula can be used when the population standard deviation is known. But how about if the population standard deviation is not known? To get around this problem, an alternative option is to select a pilot sample, that is, used explicitly to estimate the population standard deviation. Let us look at this example where the population standard deviation is unknown. Jackson's Convenience Stores. Consider a situation in which the regional manager for Jackson's Convenience Stores in Oregon wishes to know the average gallons of gasoline purchased by customers each time they fill up their car. Not only does she not know the population mean, she also does not know the population standard deviation. She wants a 90% confidence level and is willing to have a margin of error of 0.5 gallons in estimating the true mean gallons purchased. The required sample size can be determined using the following steps. Step number 1, we need to specify the desired margin of error. From the problem, we have 0.5. Step number 2, we need to determine an estimate for the population standard deviation. A way to do this is that the manager could select a pilot sample of 20 fill-ups and record the number of gallons for each. So, assuming these are the values, the estimate for the population standard deviation is the sample standard deviation for the pilot sample, which is computed using this equation. And now we have a result of 4.85. Step number 3, determine the critical value for the desired level of confidence. The critical value will be the z-value from the standard normal table, as can be seen in the previous video. So with 90% confidence level, it gives us a z-value of 1.645. And finally, we can calculate the required sample size using equation 8.6, which would then give us the required sample size of 255. The required sample size is 255 fill-ups, but we can use the pilot sample as part of this total. Thus, the net required sample size in this case is 255 minus 20, which is equal to 235. Confidence intervals for the population proportion. The previous sections have illustrated the methods for developing confidence interval estimates when the population value of interest is the mean. However, you will encounter many situations in which the value of interest is the proportion of items in the population that possess a particular attribute. In this case, from the confidence interval general format, the critical value can be taken from the z-value and the standard error as the square root of some equation. Equation 8.10 shows the formula for computing the confidence interval estimate for the population proportion. Let us see an example. Suppose a random sample of 100 people shows that 25 are left-handed. And we are tasked to form a 95% confidence interval for the true proportion of left-handers. So we have the proportion 25 over 100 for the left-handers. It is 0.25. And we have the standard error computed by the square root of some formula, which gives us 0.0433. And the proportion population estimate is then 0.1651 to 0.3349. And we can 95% confidently say that the true percentage of left-handers in the population is between 16.51% and 33.49%. So a recap of what we have learned. In this chapter, we have illustrated the estimation process, discussed point estimates, and introduced the confidence interval estimates. We've also discussed the confidence interval estimation for the population mean, wherein the population standard deviation is known and when it is unknown. We also addressed on how to solve for the sample size and discuss confidence interval estimation for the proportion. Here is the figure to describe what we have discussed in this chapter.